How to understand multi-qubit quantum measurements. Imagine trying to watch a complex dance where many dancers move together or separately. Quantum measurements on multiple qubits are just like observing this dance, but with tiny particles that follow strange rules. Let's break it down step by step. First, think about a single qubit, which is like a coin that can be heads, tails, or both at once. When you measure that coin, it will land on heads or tails, and the superposition collapses. The chance of each outcome depends on the amplitudes or the weights of the superposition. Now, when you have more than one qubit, it gets more interesting. Multiple qubits from a combined state, which is like a big dance with many dancers. This state is written as a vector in a larger space called the Hilbert space, made by combining each qubit state. 4 qubits there are for basic states, both 0, first 0, second 1, first 1, second 0, and both 1. The overall state can be a superposition of all these possibilities. When you measure just one qubit in a multi-qubit system, you need to focus on the basis relevant to that qubit. The measurement outcome depends on the sum of the amplitudes of all states where that qubit is either 0 or 1. After the measurement, the entire system collapses into a smaller state that matches the result. This is called projection, and it means the measured qubit becomes definite, while the others are affected based on the measurement outcome. The process uses measurement operators, which are mathematical tools that help determine the probabilities of each result. These probabilities follow the Born rule, which says that the chance of an outcome equals the squared magnitude of the projection of the state onto the measurement basis. There are different types of multi-qubit measurements. Full system measurement looks at all qubits at once to get complete information. Partial measurement targets only some qubits, which is useful in error correction to fix mistakes without disturbing the whole system. Mid-circuit measurement happens during the computation to guide the next steps. And joint measurements on entangled qubits, called Bell state measurements, are key for quantum communication like teleportation. Measurements can also be done using Pauli operators, which are special matrices like X, Y, and Z. Measuring the tensor product of these operators on multiple qubits reveals information about their combined properties, such as parity. This is important in quantum algorithms and error correction. In practical quantum circuits, understanding how to measure multiple qubits helps in designing systems that perform complex tasks. The timing and method of measurement influence the accuracy and coherence of the quantum information. By carefully choosing when and how to measure, you can extract meaningful results while preserving the delicate quantum states. So, multi-qubit measurements are like observing a multi-layered dance, where each move influences the entire performance. They extend the simple idea of measuring one qubit to a more complex picture, involving projections, probabilities, and the impact on the whole system. This understanding is fundamental for building effective quantum circuits and advancing quantum information processing.